Hi everybody, this is Cal with sections 12.5, Equations of Lines and Planes, and 12.6, Cylinders and Quadric Surfaces. We're going to start here with section 12.5, which covers how to find equations of lines and planes in 3-space. There's a main idea here with the beginning of this section with lines, which is that there are two things you need to know in order to make an equation of a line. You need a point that that line goes through, and you need a direction that line goes in. So think of that as a position vector, r0, for the point, and a direction vector, v, for the direction of the line. Once you have those, you can create, well, there's any number of forms here for the equation of the line. You absolutely need to be familiar with the vector equation, given at the top of 841, the parametric equations, given in the middle of 841, and the symmetric equations, given in box 3 in the middle of 842. You need to be familiar with these three different formats. You need to be able to shuttle between them. Examples 1 and 2 are examples of just working with these basic formats to come up with equations of lines. Box 4 in the middle of 843 gives just a general formula for how to find the line segment from one point to another. That can be useful, but at the same time it's better to understand the overall theory of the section. So, if you don't bother to memorize square 4, you're not too far off. Example 3 is a really good example of working with lines once you have equations for them, and I urge you to pay special attention to this example. There's some cool stuff going on here. At the bottom of 843 we go into planes. Just like there are two things we need to get an equation of a line, that being a point it goes through and a direction it goes in, there are two things that we need to find an equation of a plane. It's going to be a point that the plane goes through, and what's called a normal vector to the plane. That's a vector that's perpendicular to the entire plane, or perpendicular to every vector in the plane. Normal is another word for orthogonal. That's a little bit confusing as notation because normal can also mean length 1. So normal is a little bit of a dangerous word. You need to know the context when you're using it. But when we talk about a normal vector in the context of talking about a plane, we're talking about a vector that is orthogonal to everything in the plane. If you look at equation 5 over here, you see that what's going on is that any vector in the plane, which has format r minus r naught, should be orthogonal to the normal vector n. So literally n dot r minus r naught is 0, and that's literally the equation of our plane. It's defined by the fact that everything in the plane is orthogonal to the normal vector. Make sure you understand where this equation is coming from. It's really pretty simple. Equation 7 gives the scalar version of the equation through the plane, and 8 gives what's called the linear equation. I'm a big fan personally of the scalar equation and the linear equation because you can just read your normal vector right off of them, and that's usually what you're interested in. And 7 has the bonus that you can read off a point in the plane as well. But those are not usually too hard to find. It's not as important to be a stickler for different formats in planes as it is in lines, but be aware that you have some different options here. The rest of the section is examples of finding equations of planes. These are pretty important. This also goes through the idea of showing that two planes are parallel, or more generally talking about angles between planes, which is a pretty easy concept, so make sure you know how it's defined. And finally, when we get to example 8, we get into the idea of distance from a point to a plane, which is a good example to work through. They kind of work out a lot of formulas here that can be useful. And I urge you to draw some pictures and figure out why these formulas are the way they are. I wouldn't say that you need to memorize the formula, but this could come up from time to time, so at least know where it is, know where to look it up. Example 9 and 10 expounds on that idea by finding distance between parallel planes, distance between skew lines. and those are good examples to read as well. That ties up section 12.5, and we're going to go right on to 12.6, which is called cylinders and quadric surfaces. Now, what I want to say about this section is that I don't want you to memorize all sorts of different cylinders and quadric surfaces and so on. I want you to work through a few examples here, and I want you to understand the basic techniques in this section. So, understand what a cylinder is. You don't need to pay attention to this idea about rulings. Work through example 1, example 2. They're nice and easy. And we've actually talked about stuff like these two examples in class. Now, quadric surfaces, understand what a quadric surface is. And the big idea that I want to get across here is the idea of traces. So make sure when you're reading through this section you understand what a trace is and how to use a trace to get a sketch of a surface. So working through example 3, example 4, and examples 5 and 6 are what I really want you to spend your focus on in this section. And I really like these pictures in the middle of page 853, where it's showing how the traces fit together when you're sketching the overall surface in example 5. What I don't want you to stress about is the names of the different quadric surfaces. I don't care which one is an elliptic paraboloid, and I don't care which one is a hyperboloid of 1 sheet or 2 sheets, or a hyperbolic parabola. You really do not need to memorize any sorts of forms. I just want you to understand what traces are and how you can use them to get at visualization. So when you're looking at the later examples in the section, don't worry about identifying. Worry more about getting a basic sketch of the surface. So you can see a few more examples here in example 7 and 8. And you don't have to worry too much about applications for our purposes. So that covers 12.6 as well.